So let's see. Good morning and just afternoon, everyone. Today I'll be leading an interactive session on best practices for scientific programming. I think you all saw a recorded version of me last week, but here I am, I guess, in the flesh virtually. So I'm James Finley. I'm an associate professor in the Division of Biokinesiology and Physical Therapy at USC. A little bit of personal background. So my training is primarily in engineering, mechanical and biomedical engineering. After completing my PhD, I then did a postdoc in neuroscience. And as I said at the beginning, I'm currently working in a physical therapy department. So the work that I do spans all of those disciplines. I consider the work we do within the lab to be very interdisciplinary, and this is one of the things I've been most excited about as a member of IMSI. And today we'll talk about one of the things that I think is most important in the research process, and that's really making sure that you employ best practices for programming. So we're going to cover a few different topics today. We have for the next hour and a half. We'll do some hands-on examples if you're able to follow along, and I'll just want to plug the link in the chat to the Google Drive folder. So I will actually, let's see if I can, there. So I just uploaded a few additional files to that Google Drive folder. What you hopefully all had a chance to review was the PDF on principles for reliable and efficient and adaptable coding. I've added a PDF of the slides that we're going to cover today, a few MATLAB files. So we'll run those as an example of how to take your data analysis pipeline and separate that into individual scripts. And then finally, there's another PDF that is a paper on 10 simple rules for computational modeling. So if you do modeling as part of your research workflow, this is almost like the modeling Bible for me in some sense. I won't be talking about that today, but if we have time and people have questions, I might highlight a few key points from that paper. Okay, so let's motivate why we are here today. One thing to keep in mind, or that I'll maybe start with, is that in my program, my master's and PhD in biokinesiology at USC, I teach research methods for all of our first year graduate students. And we spend many weeks introducing students to scientific programming, primarily in MATLAB. So a lot of what I'm going to cover today is taken from snippets of that course. So there's going to be a lot of stuff we don't get to, but happy to point you to resources if you have questions. We're going to show this again at the end, but feel free to go ahead and sign in for everyone who's here today. The QR code should take you to the sign-in form, and I believe there are some questions to answer that I think will be best to answer at the end of today's session. So again, I'll bring this up at the end of the session, but I wanted to put it here in case people want to sort of get a head start. Okay, one of my favorite analogies that I've heard about certain types of science is that in some cases, the science that we do is like a house of cards. And there are two key features of a house of cards that I wanted to highlight. So on the positive side, I think a house of cards is these can be beautiful and elegant structures, right? They have nice symmetry. There's something about the fact that they exist that is impressive. But the dominant feature of a house of cards is that it's really fragile. And the first time I heard this analogy used was when someone in a seminar presented a set of results and those results were based on a lot of weak results from other studies. So this is the way that we do science, of course, is that we build a foundation from existing work, and we try to extend that work in novel and interesting directions. However, our ability to do, good, rigorous science depends on building from a really strong foundation. And so, in one, maybe dominant sense, that strong foundation is the quality of prior work. Within our own workflows and individual studies, right, our conclusions require that all the steps in our reasoning, study design, and analysis process are also very strong. And so today we're really going to be focusing on the analysis part of that structure as we build or try to draw conclusions about our own science. So let me see if I can do this here. So I'm going to stop sharing just to do a quick informal poll. So I'm trying to see, I see we have some faculty here, which is great. So this is a poll for anyone who has published any papers in your career. So the first question, and you can answer by using the React feature in Zoom to raise your hand. Has anyone had an experience where they've submitted a paper, received feedback maybe months later? The reviewers requested that you make some changes, either running new experiments or reanalyzing your data. And immediately, as your response, immediately panicked because you realized that your data and or code was not well organized. So if you've ever had that experience, please raise your hand. I think this is important for those of you who are for the trainees in this program. You're often at the very early stages of your research and you're not necessarily thinking about the end game, but ultimately we want to publish our work to make it available to the field so that, again, we can progress our science. So I'll just go ahead and raise my hand here. This is probably one of the worst experiences, or worst parts of science for me when this happened in my days as a graduate student. I was really excited. I submitted my first paper. I was really excited about the results. And then the reviewers came back and had several questions about the analysis. And I had to go back and reanalyze my data. And so the next slide, I think I have, I'll just make sure I have it here. Oh, okay. So I'll let me reorder this slide real quick. All right. So there we go. Reshare again. You can lower your hands. And so the problem was that my files looked something like this. So in other words, I had many different files, whether it was data, actual analysis scripts that I used to create the figures, drafts of analysis scripts that I no longer use, and it was all sort of jumbled in one or more folders. And so going back to sort through this was an absolute nightmare. So I asked another question. So this will be the last one. Again, for the maybe postdocs or faculty who are here, have you ever had a student defend or leave your lab for other reasons and realize that you would like to go back to that data and maybe make it available to a new student, or try to publish that data on your own? Has anyone ever had that experience where you realize you didn't really understand how your own student organized their code or data? Hey, so you all are better than I am. So thank you. We have one who co-signed this experience. So the other experience that motivated a lot of what we have discussed today is I've had students who defended. Maybe we were working on their papers, or maybe I decide later on a new student or postdoc comes along, and I think about previous data that we've collected that I want to make available to an existing student or a new student. So again, that's really hard to do if things aren't very well organized. So that's where we're really going to start today. So in the paper that I shared, one of the things that they start with is this idea of different steps in your data analysis and programming workflow. And the laser pointer. So I'm going to walk through a couple key points from this figure here. One of the things that we often start with, whether you have existing data or maybe even if you're doing simulation work, we often start with what we might consider to be more of a phase of exploration. And here they use the term prototyping. And one of the I think important things that at least I've observed over time is that in many cases in our science, we may not actually leave the prototyping phase. So we add different, test case or different analyses to a single script. We might reuse existing code, and we end up with something that works at the time, but we don't necessarily take the time to refine it, make sure it's robust, and make sure it's able to be shared. So one of the big themes for today is that as you move through your science, while it's perfectly fine and really expected to start in a prototyping phase so that you can move quickly and try to get things working. Ultimately, what you want to do is always make sure you move your code base and files to what we might consider a more development level of quality. And so we'll talk a little bit about how we can ensure that the code we write is of high quality. And ultimately, we won't really have time to talk about this today, but what we should all be doing is really sharing what we do at the end, right? So a lot of the work that we do personally, right, from my perspective, is funded by taxpayer dollars and therefore should be made available to the public. But in order to make your data available, accessible, and usable, you do need to spend some time making sure that things are documented and archived or saved in a way that's easy for people to understand. And so we'll give some examples of how we do that in my lab as we go along. If you have questions as we go, feel free to just unmute and pose them or drop them in the chat. You don't have to just sort of listen to me ramble on as we go. All right. So this paper starts with 10 principles for research programming. And we won't talk about each of them individually, but I do really like how the author separated these principles into things related to the organization of your code. And really this is both, I think about this as files in general, that could be data or code. Once your code is organized, how to make sure that it's reusable. So really thinking about the quality of your code. And then they end by talking about collaborative programming or coding. So we won't get to this last part, but this is a really important principle. Use others in your lab, whether you're learning together or you have more senior members who you can go to ask questions. Programming and science in general are not one person sitting in a dark room and sort of thinking and working by themselves. And definitely this is really a team event or process. Okay. So I think most everyone here is probably doing some sort of experimental work or building on experiments that someone else has done. And before we talk about the data or the code, I think it's really important to make sure that you have your experimental protocol documented really clearly. So, we write very detailed experimental protocols just in Word files or Google Docs that list every step of the experiment, what we do human subjects research. So what were the actual verbatim instructions you give to your participants? How do you consent them? What are each of the steps in the experiment and so on? In recent years, we've gone even further than this by adding screenshots to indicate the software we use, which checkboxes you need to select, and so on. I tell all my students, I have never seen an experimental protocol that is too detailed. So you should, never be shy about adding detail. because ultimately, to me, the best case scenario with a protocol is that senior student, can give their protocol to somebody who is new to the lab. If that student understands how the basic equipment in the lab works, they should be able to just go through and follow, A, B, C, D to execute that senior student's protocol. And when we are doing this, in the most rigorous way, we will have another student execute a new protocol written by a given student in the lab. So one of the reasons why this is helpful is because when you actually have somebody try to execute your protocol, they will very quickly identify things that are not well defined. So this is a really useful process. So then we're going to keep that protocol somewhere accessible, Google Drive, OneDrive, whatever it is, so that it can easily be shared. All right, so the next thing, a lot of this sort of foundational information is I think it's boring, but some of the most important steps in the process. As I mentioned earlier, when I was a PhD student, and even to some extent as a postdoc, I didn't really have a defined structure for organizing my code and data, right? I sort of came up with a new structure sometimes for different projects, for each new project. So if you haven't done so already, I highly recommend defining a structure for your study. So as an example here, we have you can give your study some name. For our work with human subjects research, we might have a folder for each individual subject where maybe that subject's data is included in the folder. Maybe individual code. I'll show an example of exactly how we do this for my lab later. We then might have a folder for our group data. So once we analyze the individual data, we might store those results in a group data structure or table, and then have a separate folder to analyze that group data, and maybe a folder for your papers or presentations and so on. So the idea here is that you have a single folder that you can easily share with somebody else. And if things are organized well, they can spend some time to look through your folder and its documentation and easily understand where things are located. All right, so the next basic and somewhat boring thing that's really important is the naming and file structure. So once you have your subject folders, you want to make sure you're using that same structure for all of your participants. And one of the things that I always recommend is that we spend a lot of time designing experiments, and generally we're really happy once we collect our first participant. And most people are really excited just to get through the data collection. And again, when I was going through my training, I would often sort of wait until the end and do my analysis. But what you really want to do is once you get the first participant's data, first animal or whatever you're studying, once you have a full data set, you want to go through and do all of your analysis. And this is really useful because it will often show you parts of your analysis pipeline that aren't very well defined. And so you then refine your pipeline so that you are confident with the quality of your analysis before you go through and collect all the data. The last thing I'll say about this is the other thing you often find as you start to analyze your initial participants is that there may be something you decide that you want to change about your protocol. Maybe there's something that a feature you didn't include, an assessment that you think is important, but often you may not realize that until you go through your full analysis. So I highly recommend doing that. All right, so once you're kind of comfortable with your analysis, at the same time, you want to be thinking about what is the convention that you use to name all of your files. So we do a lot of motion capture data or studies where we use a particular program called Qualysys Track Manager. and we input a file name, and it might automatically increment the last number of that file name. So you can be really creative with these file names, but ideally, in the best case, you have a naming convention that gives as much information as possible about that piece of data. So in this case, you see this is a fairly strange naming convention, but we might have a different, one cohort that, the C stands for cohort. Within each cohort, maybe you have different groups, subjects, and trials. Okay? So you can embed quite a bit of information in your file names without making them too unwieldy. Now, if the reason why this is really helpful is because if things are machine readable, which we'll talk about in a moment, you can very easily write code that iterates through your cohort or group or subject or trial. Okay, so really, really important thing to do as before you start collecting your data is figure out how you want to name your files. When it comes to these file names, you want to make sure that they are machine readable. This is both your folder names, ideally. This is less of a problem than it used to be in the earlier days, but ideally you don't have spaces in your folder names. One important thing for those of you who are doing human subjects data is that you should never use your participant's name or initials in the file names. This is no longer that would no longer be HIPAA compliant, because then those data are identifiable. Okay? So you should have some sort of subject ID number that cannot be easily matched to your particular participants, or that a naive person would not be able to match. You want to make sure your file names have a consistent capitalization. So even though all of these file names have the same letters and numbers, they're all different, right? So if you're writing code to cycle through your data, you're going to run into errors if you don't use consistent capitalization and so on. When thinking about using numbers in your file name, so incrementing numbers, something that's very basic is you want to think about how many total subjects or trials you might have, and make sure you use a consistent number of digits for all those numbers. Why is this the case? So let's say I start naming my participants, subject 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 11. The problem then is that if I try to cycle through things by file name, subject 11 will come before subject 2, right? Because the 1 after subject. So just make sure you use the same number of digits for all of your numbers. And then last couple of things related to naming. If you want to include dates, it's generally best to do year, month, day, and then use 24-hour format for time, again, so that things are organized in a logical, consistent way. And that helps you accelerate your analysis. Okay. One of the last pieces of information to think about are what are called metadata. And in some cases, classically, these are things you might write in something like a lab notebook. But now, since we want to include as much information as we can with our data, these are usually text files. We often will refer to them as README files that have additional information that might not be obvious from just looking at your data. So you might describe different analyses you're doing. You might have information about how specific variables are coded. So if you're coding sex, you might have 1 for female, 2 for male. We do clinical exams quite often in our studies, but there may be cases where you omit part of a clinical exam so that the scoring is a little bit different. And so these are pieces of information that are really critical for somebody who takes your data to make sense of it, but are not easy to embed in your standard data files. And one way to think about these metadata are that this includes details about your methods that are useful. So if you, and this we do this frequently, right? If you want to go back to data from several years ago, you don't remember all these details, you can read the file and then get up to speed really quickly on your data. So we often will keep this with our experimental protocol so that we can easily combine data if we need to, or pass it along to a new person in the lab. All right, so I'm going to show an example of the process that we instituted in my lab about a year ago. And this is, again, motivated by the fact that, students would leave the lab. We would then want to reuse that data to answer some new question. And I would have to go, track down alumni and ask them about how things are organized, what are the files, and so on. It was very tedious and, often failed because of the amount of work required. So this is just a Slack message that I shared with my lab about a year ago. And so what we currently have is what we call an offboarding checklist. This is for students who are preparing to defend or graduate. This is for me, literally what I do is you need to have all of these things organized and we need to go through them together before I sign off on your defense. Okay? So it's a requirement for graduation in my group. So for our work, we often have a set of physical documents. So if you're doing human subjects research, you have consent forms, other forms you might use for your IRB. You might have data collection sheets that you're manually completing as you perform your experiment. Maybe you have clinical exams that you're doing on paper. And so there are going to be some set of physical documents associated with your work. So you need to have a README file that explains, what those documents are and where they are located. Often each student will, compile all their physical documents in a binder that is for that one particular study. So literally, even right now, we are going back to data that were collected maybe 8 years ago and using these physical documents to make sure to interpret what happened in each of the files from their experiment. Then most of what we do now are digital files. Those could also be clinical exam data. So we might use something like REDCap to collect some clinical exam data, and then our experiment data. So how we organize that data in our lab is that we often will use MATLAB or Python or Unity, many different languages to run our experiments. So we have a folder that has the code for those experiments, with a file that explains how to run them, another folder for our data, another folder that it contains the analysis scripts. In some cases, we do simulation work or computational modeling, and we have a separate folder for anything that's a simulation-based project. Okay. So I'll show how this looks for us and then open up for any questions. So let me switch here. All right, so can everyone see this SharePoint folder? Great. All right, so this is a folder that was created by a student who graduated a little over a year ago. And so this is one of her two of the aims from her dissertation were experimental. And just as I highlighted on the previous slide, we have separate folders for the experiment, data, and analysis. So if I go to my experiment folder, I see a couple folders and a couple files. So what I do first, if I was to give this folder to a student or a postdoc, that person would first go to the README document here. And here the student has a link to a GitHub that contains all the code to run the experiment. In this Word document is a description of each of those files on GitHub, the file name, what the file does. And then we move on to explain the contents of the folder that we just saw. Okay. So there's a folder called experiment documents. Here's what those are. There's a folder called QTM settings for our motion capture. Here's what's included there. We have an Excel file for our participant demographics, and here's the information in that Excel file. So again, documentation is one of the more boring parts of research, but once things are really well documented, it makes your life tremendously easier and also helps make your data and work more available to your community. Okay, so that's an example for the experiment folder. We then go to data. So same thing, there's a README file for the data. In our MATLAB folder, we might save data for each individual participant and data for the whole group. You want to explain what each of those map files is, what are the variables that they include, what are the units, and so on. So again, I've never seen any set of data that is overly documented, right? I've never, you can almost never provide too much information for a future user of your data. Okay. So just to maybe make this a little bit more real, so just this year, one of the members of our lab, we were interested in a research question related to control of balance in people post-stroke. We were thinking about a study design and then realized like, oh, we already have data that we could use to answer this question. So I literally pointed the postdoc Sriram, he's probably here, pointed him to this folder, said the data are here, take a look at it. And then the next week or 2 weeks later, we had results. Right? So he was able to go through without any additional help, make sense of the folder, how the data were organized, and then run some analysis on that data. All right. So I want to just pause here to see if there are any questions by anyone in the audience.
Do you have a way in your lab that you, like, after you have each individual create these folders, that you then keep track of the different types of data that you have across your lab for future potential use cases?
Yeah, that's a no is the answer. That's something that
It's really tough.
yeah. So it's something that I've thought a lot about this year. So in other work that I do, we are actually doing, trying to develop some sort of best practices for data, collection, saving, sharing, and compiling across different studies. And in just doing that, it's made me realize that, oh, wow, we have, terabytes of data that could be really useful to answer some of the current questions that we have. But the data was not at the time collected, stored, documented for future use, right? We thought about it only for that particular project. So we're literally going back through now to organize some of our existing data. And it's nice because I'm starting to think much more about research questions that we could answer with existing data because it's much less resource intensive.
Awesome. Yeah, thank you. Yeah, the compilation across individuals and everything is such a huge problem.
Mhm.
But having it so organized like this within individuals is seems very helpful.
Yeah, and so in our experiments, we collect tons of data from people, right? So we do full body motion capture often. We have ground reaction forces from our treadmill, and we might have them doing clinical assessments, cognitive all sorts of things, and we sort of answer a couple of questions, and then the next person comes in, collects a whole new set of data. So we also want to make sure that we're not, or be mindful that we're not sort of wasting data. Other questions? Um, okay. So now I know that, let's see, we have at least one watch party. Um, we may come back to do this at the end, just because you might need to do some breakout rooms. Let me just get this. Victoria, do you know how many people we have here? Okay.
We have 27 attendees, but three of those are watch parties, so I'm not actually totally sure how many we have,
Okay.
or four of them.
Are you able to create a breakout room or
Yes.
breakout? Okay.
Yeah, and
Can
I'll
we
make it closed.
do, let's see, 6 breakout rooms?
Hmm.
And we'll just do this for 5 minutes. So there are a few questions here that hopefully you all can see. And minimize my Zoom. So in these breakout rooms, you're going to be, of course, mixed across labs, but I just want you to spend a few minutes answering these questions. And, the answer may be no to the first question, but I want everybody to spend a little bit of time to think about how you might be able to implement some of these principles for data organization and file management in your own work. So the first question is, do you know if your team uses a defined convention for organizing files and naming them? What are some ways that you might improve your team's standards? And then are there any personal strategies that you use that we haven't discussed so far? So we'll do this again, we'll do this in breakout rooms for 5 minutes each. Okay, so we'll take just a couple of minutes here to hopefully get some volunteers to share. So, does anybody want to volunteer to describe a convention that you might use in your own lab for file organization and naming?
Hi. Ours is pretty much exactly what you described that we use here at UCI. We put in subject name, trial types. If it was collected over multiple days, we'll put the date in. Um, I don't know what else. I think we typically use like underscores to separate each of those sections, but very similar.
Great. Anybody else use anything different?
Part of what I was talking about, my name is Bert Tanner. I'm a faculty member at Washington State University, and we do a lot of like muscle mechanics, single fiber type work. And I was telling the people in my breakout group that we're like very regimented and organized in terms of our data acquisition and what we do with where we store our data, how we name our data. But then once it goes into like the analysis pipeline, that's like totally not consistent at all. So I was thinking about when we were asking these questions, like there's two halves of the coin that we have where we're really good at where the data is and how it's structured and how we organize it with like, what species it comes from, what date the dissection was done on, when the
Mhm.
experiment was run, things like that. But then as it goes into like different people analyzing it, it sort of takes on its own form that they put on it, which, that has some advantages for flexibility and freedom of thinking for those people, but it also is impossible to like keep up with and repeat if you need to go back to it, like you were talking about. So,
Yeah, yeah. This is the reality of our science is that especially when it comes to analysis, right? We're rarely working in a team at that point. It's often a student, a postdoc, an individual faculty member who's writing the code for the analysis, and they have their own, um, sometimes standards, sometimes things they make up on the fly. And so we'll talk a little bit as we go on. Even if that's what you do, you can still document those things, make sure your code is well commented, and then optimize your code so that somebody else can understand it. Okay. Does anybody have any personal strategies for file or data management that we haven't discussed so far that they'd like to share with the group? Okay. the last thing I'll say on this topic is in recent years, one of the things I've noticed just in teaching is that students, graduate students, often will come into my class. Maybe they don't have programming experience. And when I start to share files with them, either, on our, it used to be Blackboard, it's Brightspace now, or maybe they collect some data in the lab. I share scripts with them. I started to notice that students would just like keep everything in the downloads folder, which was really strange to me until I realized that a lot of people's, use of technology is primarily driven through their phone, where you often will just save things essentially to your downloads folder. So the idea of creating file structures and doing things really systematically was newer for many people than I initially expected, and than it was, 10 years ago. All right, so now let's move on to data analysis. So now that you've designed your experiment, your data you're starting to collect data, you have good file naming and file management strategies. What are some things to consider as you start to try to draw inference about your scientific question? So generally, I like to outline several steps in the typical data analysis pipeline, and I'll highlight some of these as we go. The first is making sure you know your data, know what you're trying to do. This is often the hardest part for people who are new to science or data analysis. You then need to import your data into some environment. We're talking about programming today. You want to do some quality control, do what we might call pre-processing, computing summary measures, make figures, do stats, and then save the results. And one of the things that I really try to highlight in my group is that steps 3 through 9 should really be automated and as concise as possible, as we'll discuss later on. All right, so what does it mean to know your data? It's really, when you do things from scratch, often just by nature of moving things forward, you will have a very good understanding of your data. But often you might join a group where the data already exists, or you download data that exists from prior studies. So things you want to make sure you understand. How were the data collected? What was the exact protocol? What was the hardware that was used? Because that might influence different properties of your data. For a lot of the work that we do, we deal with time series data. So things like force, EMG, marker positions, what have you. Time could also be multiple measurements over days. So you always want to make sure that you know the frequency with which or at which your data are sampled. So if you have 1,000 data points, how far apart in time are those data? That is not all, you don't always have a time, vector that corresponds to your data. So if you don't, you need to at least know your sample frequency. Another thing that is often, not embedded in your data are the units. If you just have a matrix, right, that those are just sets of numbers. Always make sure you know what units you're dealing with. This happens all the time where people are thinking they're dealing with meters and it's millimeters. They think they're dealing with degrees, but it's radians. You think the data are in percent, but they're fractional, right? So really basic thing that's really important. And then the last thing, which we won't have a lot of time to talk about today, is accuracy and reliability. So just because you have numbers does not mean those numbers are an accurate and valid reflection of the thing you're studying. We do metabolic testing quite frequently in our research where we measure oxygen consumption. And if I have somebody walk at 1 meter per second for 6 minutes, and I look at the metabolic data, right, it's highly variable. That is both a property of the measurement system and the physiology. So you really need to understand how much of the variability in your data is true physiological behavioral variability versus variability due to your methods and equipment. So when talking about variability, again, when we have variability that's due to our methods and equipment, we're generally talking about errors. So hopefully, this may or may not happen in a summer research experience, but you're receiving some training to perform to do your experiment, and hopefully you have some sense of how reliable your methods are by essentially. You might do this by testing the exact same participant under the same condition 1 week apart, right? Where you would expect the same behavior and outcome, and you can, do formal assessments of how reliable those outcomes are. For your measurement instruments, if you have some flexibility in the tools you use to make your measurements, make sure you understand how accurate and reliable those tools are. And then lastly, we're all studying some aspect of human and animal behavior. And so you want to think about potential sources of variability in the actual signal that you're measuring, right? So what elements of that variability are due to the things you're controlling in your experiment? So let's say speed, if I'm walking, versus things that are not critical to your research question. So for instance, getting used to walking on a treadmill might not be part of my research question. So I want to make sure that I have a sufficient acclimation period so that does not influence my measurements. Okay. The last things about knowing your data are understanding the format that your data are stored, and what we already discussed today about how individual files are organized. So across all of our labs and studies, you may run across different file formats. So just some basics for if this is new for people. One of the biggest differences across these formats is whether they are proprietary or able to be used interchangeably across different platforms and pieces of software. So in general, you want to save data in formats that are interoperable across or independent of your analysis software. So things like CSV files, to a certain extent Excel files, and even sometimes JSON files can be read in any programming language, or in some cases imported into statistical analysis software. Even though we'll talk a lot about MATLAB today, MAT files, which we use in MATLAB, and for motion capture C3D files, these particularly MAT files are proprietary in the sense that they are built only for MATLAB, and you may not be able to read them into other pieces of analysis software. So, talk with your PI about the types of file formats and the pros and cons of these different formats for your purposes. Ultimately, my goal is for people to share their data. I don't care if you share it as a MAT file or a CSV file. Sharing something is better than sharing nothing. So just keep that in mind. All right. So the next step in your analysis process is to really clearly know what you're trying to do. And so I separate this into a few different questions. So the first thing is that you shouldn't collect data just to have the data. That data should be collected to answer a particular question. So you need to know what that question is and be able to state it really clearly. So as you're starting to develop analysis pipelines, if you're new to this, this is essentially like, solving word problems in algebra in middle school, right? So you're going to have a research question, which is a word problem. You're going to start somewhere. You have some measurements that you've made. Then one of the things that people sometimes forget is, well, how do you know if you've answered your question? In other words, on the back end of your analysis, what is the figure you're going to create? What is the number you're going to compute that allows you to know if you've answered your question? And so you always need to keep that in mind. Then you want to write or at least think through the step-by-step procedure for going from input to output. So this is what I refer to as the development of your analysis process or algorithm. And so you're gonna have a bunch of steps to go from input to output. Now, again, one of the kind of burning topics of the day that we don't have a lot of time to cover is when is AI useful in your data analysis process? Okay. So we probably all have differing opinions about this. I think that once you get to this step, if you are new to data analysis, this is a very good use of AI. Is here's my research question. Here are the data that I'm collecting. Help me write a set of an analysis process to answer this question. Right? I'm using MATLAB. I'm using Python. I'm using these packages. Highlight potential functions that might be useful. Okay? So you're using, AI like a colleague to help you lay out your process. Or maybe you have an algorithm or a set of steps that you've outlined yourself. You can help use AI to understand what are the strengths and limitations of those steps. Once you know what you're trying to do and you have a roadmap, then you want to convert that to code. Okay, so this is for people just starting out. These two steps are the hardest thing that you're probably going to do. And again, we can argue about the use of AI. So you could, in MATLAB, in Copilot, in Claude, just ask it to write your whole analysis script. Here's where I'm starting. Here's where I'm trying to go. Write an analysis script to do this. And it's going to give you code. The code's probably going to look great. But it's often going to be a lot of code that you then have to interpret and quality control. Okay? So my belief is that you definitely do not want to just ask for the full process, but you can use AI as a consultant as you go along to help you write accurate and efficient code. So common things that you're going to be doing at these steps. Once you start writing your code, you need to define some variables. You might apply a function. This laser pointer. You often will have a set of numbers where you need to extract certain elements. So you need to define rules to extract those elements. Maybe you have interactive code where, I use this for quality control sometimes. So lots of different things that you might think of. As a general rule, what I tell most of the people I work with is that, again, we primarily use MATLAB, but if there is something that you think could be done with code, there's a good chance you can do it with code, that somebody else has already done it, and that code exists. Either it's built into MATLAB or it's something that you can download from the web. Okay? So try not to reinvent the wheel if you can help it. Okay, basic things, you always write a snippet of code, check that it works, save it, move on. Maybe, I don't know if we're going to have, Victoria, do you know if we've ever had a GitHub tutorial for MC? Or does anybody?
We have not,
What's that?
We have not, but that
Okay.
is actually a great idea.
Okay. So version control is, you can do what's called version control in different ways. What version control means is that as you change a file, you save a history of those changes. The most basic way to do version control is once your code is working, save it with a new name, and then start working on that new file if you add new features, right? So the old version it still exists. Nowadays, you can use GitHub for a lot of this stuff. Maybe we can talk about that later this summer. I am not a GitHub expert. This came about after I learned all of my bad habits, but super, super useful, both to organize your code, share code with people in your lab, and to do version control. Okay, so All right, so we just have a few slides left, and then we'll go through some examples, a few hands-on examples. One of the things that for people who are new to programming that I have observed over the years is if you come from a field, a background where most of your training has to do with, I'm going to say, sort of memorizing information, you know, making written arguments, right, and not programming. Programming is a very different type of learning than what you might be accustomed to. Specifically, you learn mostly through negative feedback. So you write some code, you run it, you get an error message. If you have your audio on, you will get some sound from MATLAB, and it will maybe drive you crazy. The thing to keep in mind is that these messages are, yes, they're frustrating, but they are meant to help you fix your problems. Again, nowadays you can, even within MATLAB, so MATLAB has an AI tool, Copilot, built in. You can ask MATLAB to help you identify the source of the problem, interpret the words in the error file or error message, excuse me, and suggest ways to fix that error. Okay. So negative feedback is your friend. It's helping make sure that your code operates, at least helps you make sure that your code runs. And then it's up to you to ensure that it runs properly, which we'll talk about shortly. All right. Last few things here. So one of the things that you need to always do is to make sure that your code is correct. Okay. So one of the biggest problems I have seen over the years, and I continue to see, is when people run code, that code produces a result. Because there are no errors and the result looks plausible, people think the result is correct. Okay, so plausible is not the same as accurate. So here's an example where you have two vectors here, x and y, and I'm going to make a plot. I want to look at the relationship between how people score on some exam score changes as a function of repeated testing. And you get a figure that looks like this. So my axes are labeled correctly. I have a figure. I didn't get any errors, and you might conclude that, oh, with practice, people get better, right? The scores go up over time. That is a plausible result, and you didn't get any errors. But this is wrong, right? If you look closely at the code, you might be able to find what this error is. I'm supposed to be plotting the x variable on the x-axis, the y variable on the y-axis, but I'm plotting the exact same variable on both axes. When you fix the problem, so here, my second input is now y. Now you see that there's some variability from session to session, but no clear trend. Okay? So very basic example, but always keep in mind that the lack of errors does not mean that, or the lack of an error message does not mean that there are no errors in your code. All right, last two slides here. Things that you want to do, and let me actually make this a little simpler. Okay, so some of this is maybe more useful for people who have more experience. Try not to write really long lines of code, right? It may work, but it's not human readable. Always think about making code that is as human readable as possible. So that often will involve breaking up things that are complex over multiple lines of code. I like to really bold this. Variables like x, y, I, j are not useful at all. Like, stop doing that. We all start doing it, especially writing for loops for I equals blah, blah, blah. Nobody knows what I is. So just give it a meaningful human readable name. So for example, I'm cycling in a for loop through different participants. I just use my looping variable, which normally you might call I, just call it participant. Right? Then it's really easy for somebody to read your code and say, oh, this loop cycles through the participants. One of the, I'm not a computer scientist, but I've heard this stated multiple times from people who have more formal programming training, is that really well-written code does not require a lot of comments. Okay, so again, if you use human readable variable names, you break your code into individual lines, it becomes very easy to see what's happening so that you don't need excessive comments. Okay? You should always still add comments as you write your code, but using, like I said, meaningful names goes a long way to making your code easy to understand. So a couple of things that we're going to do now are talk about ways to organize code and make it more concise. So using functions is a big part of that. For those with experience, and again, we'll do a by show of hands here. Raise your hand in Zoom if you frequently use functions or you write functions in your code. Okay, so a function is not a script. A function has a defined name, defined inputs and outputs. All right, so we have, maybe a handful of people here. I'm going to assume that a lot of people who didn't raise their hand are maybe new to programming. So let's take a look at a couple of examples about how we might make our code more concise. So I'm going to switch to the online MATLAB tutorial that was linked in Slack that Victoria shared with you last week. And I think we are. Let's see. Okay, so most people who are new to MATLAB, hopefully you have completed what's called a MATLAB on-ramp. So I'm just going to show you how to navigate to this this resource. All right. So if I go to mathworks.com, the main website for MATLAB, I can log in with my university account, go to Learn, and go to self-paced online courses. This is one of the things I love most about MATLAB and this is sort of what universities are paying for. So they have a really great set of resources that are well organized, that are provided for you to learn, countless skills in MATLAB. So today we're going to talk about writing functions, and let's see. All right, so you can it's probably easiest. Well, I'll drop this in the chat. All right, so I just dropped a link in the chat to this course. So if you're not accustomed to writing functions, MATLAB has a course for that. It takes a couple hours, or I know this one's only about an hour, so it's pretty easy to do. So let's see, so there are two different ways or two different types of functions you might write in MATLAB. One is referred to as a local function. The other is referred to as a function file. So in the interest of time, we're going to jump right to the example. So typically when you are starting out with programming, and if you're using MATLAB specifically, your script has a set of actions that you perform, and those actions are performed sequentially, right? So you might import data, pre-process it, make a figure, export the figure, or something like that. Right? So that would be a script. So here's an example of a script in the tutorial that does just that. So there's some data about city temperatures that's first loaded into the workspace. There are specific variables that are loaded into the workspace. Then in this code, there's going to be some statistics calculated for the minimum. These are descriptive statistics about the temperature in Chicago, and then a figure that plots those descriptive statistics. Okay, so very basic analysis script. Now, let's say that I want to do the same thing, compute these descriptive statistics, and make a plot for each of these 5 cities. What you would typically do if you're often new to programming is say, copy this code, paste it, and then change everywhere it says Chicago, change that to Dallas. Then you paste it again, change it to Las Vegas. Now, that can work, right? You can do that and your code will be correct, and that's fine. However, it is a very inefficient way to code. Does anybody want to offer the reason why that is a inefficient and dangerous way to code? In other words, copying and pasting the same code multiple times and then changing, things like variable names. What's the problem there?
It's cumbersome and you have to copy paste in multiple places
Okay.
for one change.
It's cumbersome, so the code becomes longer. Monica says you will make errors. This is the number one problem is that the more you do that, the higher the probability that you forget to change something when you've pasted. Okay. This is one of the most dangerous things you can do when you program. Because often, again, as I said earlier, the code will run, you will get a result. That result may look plausible, but you may have a innocuous error somewhere in the code that's hard to catch. So instead, what you should be doing is using functions, right? If I'm going to repeat the same set of steps, then I need to use a function. MATLAB has a really cool way to convert code to a function. I just learned about this in the fall when I was reteaching this course. And this is called refactoring. So what we're going to do, it says refactor these lines of code to convert them into a function. So all I have to do is select the code, right click, and go convert to a local function. So now I can see in my script, my code disappears, and it creates a function at the bottom of the code. Okay. So right now, the function has no name, or the name of the function is untitled. It has the data for Chicago as input, and it outputs the stats for Chicago. Okay, so that's the first part. So we're going to work through full refactoring here. All right. So now we want to make this refactored code useful. So if you're new to functions, the way that a function is structured, the syntax of the function, you have the name here. Well, first you have you declare that at this point in my code, I have a function, so that these blue words are protected words in MATLAB. You then have the name of your function in parentheses, 0 or more inputs. And then on the left-hand side, 0 or more outputs or assignments. You designate end to be the last to show where that function declaration ends. And then inside you have your code. All right, so let's finish this up. All right, so now we have this local function called untitled. It's not complete yet. So first we need to make sure we're using the same, we want to give this function a useful name. All right, so this says to rename the function to calc stats. So we're going to rename it there. Now that's a more general name. Oh, I need to rename it up here. Now we need to update the inputs and the variables within this function. So now we're going to start by changing the input, right? We don't always want to operate on Chicago. We want to operate on, different cities. And we want to make sure that this variable city is used throughout the function. So there's a shortcut, Shift Enter to change the others. We're going to do that. All right. Now we want our output not to be Chicago stats. We want it to be more general. So we'll change that to stats. So now you see we have a general function that's going to calculate the statistics for any given city and output those as a variable called stats. And then now we can go up here. We can calc stats for Chicago. We can do the same thing for New York by calling our function with New York as the input. Okay. So here we can see this is a much more compact way to do the same thing multiple times than taking this code and pasting it, 2 or 5 times and manually changing all the names. Any general questions about functions? Yeah. Right. So we don't have time to go through function files. So what we did was a local function. In other words, that we defined the function in the same script where the rest of our code lives. That is most useful if you don't think you'll ever use that function again for other analysis. If you think you might use that function for other analysis, you would want to save it as a separate script. The last thing, and we'll probably mostly just spend the rest of the time answering any questions you have, is how do you make sure that your programs are correct? So oftentimes you might do this indirectly, right? You might check that certain conditions hold when you write your code, that there are no errors, that the results, again, look plausible. However, you can be a lot more direct about how you check and verify whether your code is correct. And so I'll show one last thing in the MATLAB tutorials. There is, again, a sort of formal process in I want to say computer science referred to as unit testing. So just like there's a tutorial on functions, there's a MATLAB tutorial on unit testing. And the basic idea here is that you write code that tests you write testing code that evaluates your analysis code. So for example, if I wrote a function that computes the area of a circle, I might write a test script that gives a known radius and evaluates whether my function provides the right answer. Okay? So in other words, you have a case where you know what the output should be, and in your code, you verify that your script, your function gives the correct output. All right. Now, there's I think a decent amount of art that goes into unit testing, because you can test anything, right? You can provide any sort of input and any sort of output. So you really want to think carefully about what are the places where my code is likely to fail. In other words, we might call those edge cases. Do I need to make sure that I can handle or provide an error if I try to divide by 0, right? It's something like this. So as you are writing your code, you always want to think about, how can I verify that this particular set of steps is always going to be correct, and potentially give me an error, a meaningful error, when, let's say I'm providing an input that is not appropriate. So let's see, I think I can go. I'll stop there. I'll put the link in there. So you all can, I would again highly recommend going through that unit testing tutorial. I think this one might take an hour or 2 or something like that. A very helpful way and tool that you can integrate into your data processing and analysis pipeline. Okay, so to conclude here, a lot of the reason why we're covering this topic is that, writing code is a form of writing, a form of communication. And so, like all communication, you want to think about who your audience is. Most of the time, people write code and think that their audience, well, they may implicitly only write for themselves at that time. You're obviously writing for your computer because the computer runs the code. You are also writing for your colleagues. So people may use your code in the future to analyze your data. And as I said earlier, your future self. So you all are going to make sure that if I have to come back to this code in a week, in a month, in a year, that I can make sense of it. And a lot of these principles that we covered will help you accomplish that goal. So since we have a couple of minutes, I want to share one example. So there's some code that I wrote to give an example of how I like to separate different aspects of my analysis pipeline. So I will now just demo that really quickly in MATLAB. Okay, so if you go to the IMSI MATLAB, the folder that we shared for today's workshop, you're going to see a set of 4 scripts. So there are sort of there are two things that I did with the naming of these scripts. The first is that they're meant to be run in order. So I've named them in a way that it's clear what the order is. So script 1, 2, 3, 4. The second thing that's really important when you name your scripts is to use ideally verbs in the name. So the name should actually tell you what the script does or what the function does. Okay, so this is to give an example of data analysis pipelines. I'm going to simulate some data. We're going to then combine data. That's combine it across multiple participants, summarize it, and then create figures. So this is often how when I do my own analysis, how I separate my steps, and then often what I expect from people in the lab. So if you run the first, script, what this is going to do is actually to specify the number of participants. So I'm going to simulate data from 10 participants. And this is meant to represent something called adaptation data, some type of behavior that we study in the lab. Here is my simulated data. This looks like data we might collect in the lab for an adaptation study. In this script, you can look at it in your own time. I've tried to add comments that explain exactly what we're doing throughout the whole script. But the basic thing it does is it creates a folder. In that folder, I have 10 synthetic or artificial participants. Tried to use a reasonable naming convention for the folders. Within each folder, there's a file for that participant. And their data is saved as a CSV. Then I can run code to combine the data. Oops. That creates a variable called data all that just combines data across my 10 participants. I then have a script that will summarize the data. This computes different fits to the data. So we're going to extract some parameters about how fast people adapt or learn. And then finally, I have a script that creates my figures. So the key figure here is a comparison of some estimated parameter to its true value. So I can see if I can recover, something about these participants. And if you look closely at that script, it also, I think this was part of last week's tutorial that I did. We're going to create the figure, add labels, do all of this in MATLAB, export it as a PDF, and you submit that to the journal when you write your paper. So again, it's a full pipeline, all in MATLAB, synthetic data, compiling data, doing analysis, doing statistics, making figures. And then I can just share that with anybody. All right, so I'll stop there for today, and I can hang out for a minute or two if people have any questions.